Okay, now for the second page of the physics practice test. This is a lot of stuff that we would have gone over in class, so this is why I kind of made this. This kind of forces me to go over it here so you kind of see how it all works, because it's really good stuff. Okay, so number 8. Emma sees a three-legged unicorn on the road ahead of her and slams on her brakes. Draw a picture that explains why her car tipped forward during her desperate and, alas, unsuccessful maneuver. Very sad situation. So what you have to do is draw a car. That's the hardest part of the problem. I've gotten really good at it after years of doing this. So there's Emma's car. Okay, so here's just going this way, right? And so she is braking. So the force on the car, see, here's my motion marks there. The car is going this way. The force in the car then is stopping her. So on the tires, because there's a force stopping her, right? The road is stopping her. She's pushing the road forward. The road is pushing her backwards as you stop. So that force of braking is stopping the car. And as you learned in the one before this, chapter 9, things like to rotate about their center mass. So let's say the center mass of a car is somewhere down, the engine's in front, I don't know, maybe somewhere right there. That's the center of gravity or center of mass, pretty much the same thing of a car. Okay, it wants to turn about that point. We have a force acting on it, and the forces act at a radius arm of where you're pushing on the car here, and it wants to turn about there. So what you do is you draw a line from the bottom of the tires, from each tire to the top there. Okay, now you can imagine then each one of these forces has a component in this direction. Okay, I'll use a green pen or something, right? There's a component perpendicular, like that big. This one's kind of a bad picture, but there's a component that is perpendicular, like maybe maybe that big or something. That wants to turn the car this way. It's like you have a bar and you're pulling or a wrench or something, and you're turning the wrench this way. You're turning the wrench this way. Both of them, the wrenches are turning, what's that, clockwise? So the car then wants to go like this, wants to go clockwise, which means the front goes down and the back goes up. So when you brake, the front of the car wants to go down and the back of the car wants to go up. Now the exact opposite thing happens, of course, when you accelerate. So when you accelerate, I gotta draw the car again. There's the car. When you accelerate, the force in the tires is in the opposite direction. The car is pushing. You're pushing the wheels, the earth backwards. The earth is pushing you forwards. So now we draw our lines to the center mass of the car, and now it's like it wants to turn you. You can again imagine that there's a component this way. There's a component like this, perpendicular to it, and now it wants to turn the car this way. So the back goes down and the front of the car goes up. So when you accelerate, the back of the car goes down, front of the car goes up. In other words, more weight is on your back wheels, which is why friction is more important on your back wheels when you accelerate, and it's more important on your front wheels when you brake. So when you're braking, you have more weight in your front wheels, so you can get more friction and more force of friction on your front wheels, so your front brakes are more important when you're braking, and your back tires are more important when you accelerate. All things being equal with weight, where the weight distribution is and everything. Okay, so kind of cool. So those two pictures there, pretty easy. It's all about rotating about the center of mass, and when you exert a force not at the center of mass, away from it, you're going to exert a torque. A torque is the lever arm times the force that's applied. The harder you brake, the more that torque is. Okay, next. Flying upside down. Why don't they fall out? Whenever you fly upside down, the centripetal force, when you're upside down, this is to not fall out, the centripetal force, the force keeping you going in a circle, has to be equal to gravity, because gravity wants you to fall out. This is the same thing we could have said in a roller coaster, or any kind of track where a ball goes upside down. Mass is canceled, doesn't matter how heavy you are. If you want to know how fast you're going, you solve for v. So let's see, v squared is equal to gr or the velocity is just the square root of g times r. We'll say g is 10, square root of 10 times 40. That's 400. Square root of 400, I believe, is 20. So nice easy math. So 20 meters per second. So you have to go 20 meters per second, which is like what, 44 miles an hour multiplied by 2.2? Not crazy fast. 40 meter radius is well, that's reasonable size. Maybe a little bit small, but if it is bigger, you'd have to go faster because it wouldn't be quite as much of a circle. So the bigger the circle you go, the faster you have to go. But that's reasonable, and only 20 meters per second. Okay, so now a meter stick. So again, balancing meter sticks. That means the force has to be balanced on each side. The torque has to be balanced. So now the fulcrum at 40 centimeters. And again, we would have done labs with this in class if we'd had class. So, oh well, we can still pretend that we're actually doing this. So meter sticks are 50 centimeters long. So we'll put the fulcrum at 40. So somewhere in here, that's our little triangle, little balance point. That's at 40. Here we have 0. Here we have 100. And we have a 500 gram mass hanging at the 80. So let's say here's 80, so we hang 500 here. As long as everything's in grams, we don't need to worry about units. So let's say it's 500 and 80. As long as everything's in centimeters, we'll just keep everything in centimeters. Okay, so this is at 80. And what mass must Callan hang at the 10 point? So let's put a 10 here. So we want to hang some mass m here so it balances. Now one thing we have not taken account of is the 2 kilogram meter stick. So the meter stick weighs 2,000 grams. So you got to be careful of that, right? Put 2,000 in. Kilogram is 1,000 grams. Now here's the trick. Since the meter stick weighs something, we're not going to pretend it doesn't weigh something. It's as if it's hanging at the center of mass. Okay, so what we do is center mass is 50. We're assuming we have a nice even meter stick. So at 50, and we hang the meter stick at 50, and then everything works out and we can do the math. So when you have to take into account the mass of a meter stick, it's as if the entire mass is hanging at 50, at the center of mass. Now we can do the math. We have two torques that have to be balanced. We have this 50 one, which is 10 centimeters away, or the 2,000, 10 centimeters away, and the 500, which is 40 centimeters away, right? It's how far from the fulcrum. And this one, 10 away, or wait, 30 away, has to balance it. So this mass, Callan's mass here pulling down, has to balance these mass. You know, this it wants to go this way, and these masses want to turn it this way. One wants to turn it that way. They have to be balanced. So it's always the mass times the distance. This distance is 30. That's got to be really careful of that. How far from the fulcrum? Not where it is, right? 40 minus 10 is 30. So you go 30 m, that's one torque, has to balance two torques. The 2,000, 10 away, so 2,000 times 10, plus the 500, which is 80 minus 40, which is 40 away. So plus 500 times 40. So m is, what's that, 20,000 plus 4 times 5. Ooh, I think that's both 20,000. So 20,000 plus 20,000, 4 times 5 is 20 with 3 zeros. Yep, that's right. Divided by 30. So that's 40,000 divided by 30. And I get that that's equal to 1333.33, however many decimal places you want to take it. 0.33, and this is mass, so we can put grams. So you would have to hang a mass of 1333.33 grams at this point, and it'll balance those two. Okay, so again, the idea is here the sum of the torques. Torque is the force, and as long as we have the mass right, we could ignore gravity is the same everywhere. We just have to make sure the masses are all in their same units. So that would be that many grams, or 1.33 kilograms, however you want to do it. Okay. That's how those works, balancing the torques. All right, now we're going back to cars. Rose takes a turn 30 meters in her mu equals 4. How fast can she take the turn so that her car just doesn't slip? Okay, so if we're just, now it's not banked, we're going to do bank turns down here. So bank turns mean the centripetal force, the force making you go in a circle, has to be equal to friction, and everything's nice and flat, so it's just mu mg. I did a problem like this before. Mass doesn't matter. It doesn't matter how many people you have in the car or anything. So the mass cancels out. We want to find how fast she can go. We could say she wants to go a certain speed. What's mu? Or what's the radius? It just, we have to know everything but one of them. So we're going to solve for v. So let's see, put the g over there. So v squared is equal to mu gr, or v is equal to the square root of mu gr. And then you just plug in the numbers. It's pretty easy math. 0.32 times 10 times the radius of 30. So 0.32 times 10 times 30 square root. I get 9.8 meters per second. Okay, so again, centripetal force is supplied by friction. Now if you have a banked turn, so it gets trickier. So we have our car in a banked turn like this, going in a circle, right, like at racetracks. Let's see, you got to have the top of the car. Here's the wheel. Yeah, here are the tires. Okay, now it's looking better. So there's our car going in a circle. Steering wheel, but wait, we got someone in front of it. Okay. So the bank turn helps you go in a faster circle. Now the math there is pretty tricky. I was going to work it out. There's lots of places online that work it out really well. I suggest you just look at those. It's tricky. You have to take into account the normal force, the force pushing up from the surface, because that's what the friction depends on. And the centripetal force is this way, but F parallel is pulling down the slope, and so you got to take the component of F parallel along this line. Anyway, when you do that, you get that the centripetal acceleration that you can accelerate in, v squared over r, is equal to mu plus tangent theta divided by 1 minus mu tangent theta. Okay, and again, you can look online. We're just going to use this formula. You don't have to worry about where it comes from, deriving it. I kind of explained all the geometry like that. When you do it all, and if you want to see exactly how to derive it, look online somewhere. There's lots of videos to talk about it. But this is the formula you get. Now, one thing we can say is, what if there's no mu? What if it's frictionless and all you're depending purely on the banking? Then mu equals 0 is just tangent theta. So v squared over r equals tangent theta. The bigger theta is, the bigger tangent is, the faster you can go. Tangent theta gets infinite at 90 degrees because tangent's opposite over adjacent. At 90 degrees there's no adjacent. The adjacent's 0 and the opposite's infinite. So tangent gets bigger and bigger and bigger as theta gets bigger, which makes sense. You can go faster and faster and faster the more it's banked. With friction you get this mu on the top and the bottom. Okay, now we just plug in the numbers. We want to know what mu of the tires can be so you just don't slip. Okay, so we know everything but mu. So let's plug in all the numbers. You want to go 31 meters per second. So 31 squared divided by the radius is 28 equals mu plus tangent of 35 degrees divided by 1 minus mu tangent of 35 degrees. Okay, tangent 35 degrees. My calculator's in degrees. So 35 tangent, I get 0.7002. Pretty close to 0.7. So that's nice. And 31 squared divided by 28. 31 squared divided by 28 is 34.32. So 34.32 is equal to mu plus 0.7 divided by 1 minus 0.7 mu. Okay, multiply this both sides. 1 times that's of course 34.32. So 34.32 minus 0.7 times 34.32, so times 0.7 is 24.03. So minus 24.03 mu equals mu plus 0.7. Let's put the mu's over here and the 0.7 over here. So 34.2 minus 0.7. 34.32 minus 0.7 is 33.62. So 33.62, see minus, that's right, equals 24.03 mews plus a whole mu is 25.03 mews, or mu is 33.62 divided by 25.03, and I get 1.34 roughly. So 1.34, which is very high, right? We talked about most mews are less than 1 for car tires, maybe some super sticky race tires are above 1. You would have to have amazing, the best tires ever to do this. So even if it's the road is tilted at 35 degrees, you're not going to go 31 meters per second. 31 meters per second is fast, right? Multiplied by 2.2, that's like 65 miles an hour. 28 meter radius is a pretty sharp corner. So you just can't do it. You're going to have to either bank it more or, of course, slow down is the best way. So, okay, but anyway, that's how you do this. Again, we don't worry about where this formula comes from. You can just use it on a test, but then you just have to be able to use it to figure out things. Again, we just got to know everything but one. Here I gave you everything but mu. I could have said how fast can you go, what radius must it be, all that kind of thing. Okay, all right, thanks. I'll do more for the other videos. Hope this helps. And I'll talk to you guys later.